This is the AMS Weather Studies WE 101 PowerPoint Chapter 10. We're going to look at weather systems of the middle latitudes. This chapter covers a variety of topics including air masses, where they originate, North American type, source regions, and air mass modification, frontal weather, such as stationary, warm front, cold fronts, occluded fronts, etc. We're going to talk about extratropical cyclones, their life cycle, the conveyor belt model, some of the principal cyclone tracks, talk a little bit about winter storms. We're going to also deal with anticyclones and local and regional circulation systems. The chapter begins with some historical perspective on early observations on the east coast cyclones, and I'm going to let you read over some of the many notable achievements of Ben Franklin and Daniel Defoe relative to weather and their observations in the early to mid 1700s. We know from the previous chapter that the weather of middle latitudes is particularly dynamic because of the migration of cyclones and anticyclones that are embedded in the prevailing westerlies of the planetary scale atmospheric circulation we talked about. In this chapter, we examine the circulation features and weather conditions that accompany the major weather systems in the middle latitudes. And to begin that study, we have to talk about air masses. We know that an air mass is really nothing more than a large expanse of air covering thousands of square kilometers. And one of the characteristics of an air mass is that it has relatively uniform horizontal temperature and humidity. The properties of an air mass depend upon the type of surface area over which it develops, that is, its source region. North American air masses are classified in the following way. They are classified as either polar, P, tropical, T, continental, C, or humid maritime, M. There's a fifth air mass type called Arctic, or A, which is dry like continental polar, but it's much colder. Continental tropical air develops primarily in summer over the subtropical deserts of Mexico and the southeastern United States, where it brings in very hot and dry air. Continental tropical air, CT, develops primarily in the summer over the subtropical deserts of both Mexico and the southwestern United States. Maritime tropical, or MT, is very warm and humid because its source regions are the tropical and subtropical oceans, or seas. Maritime polar, or MP, are the cold ocean waters over the North Pacific Ocean and North Atlantic Ocean, generally north of 40 degrees latitude. And the West Coast MP, maritime polar, brings heavy winter rains, showers, etc. to the mountains and persistent fog in the summer. The CP, or dry continental polar air, develops over the northern interior of North America. In winter, CP air is typically very cold because the ground in its source region is often snow-covered, the length of day is short, and solar radiation is relatively weak. Arctic air masses, distinguished by A, form over the snow or ice-covered regions of the Arctic Basin, Greenland, and North America, north of about 60 degrees latitude, and this region also receives extremely low radiation throughout the winter. This diagram shows you the source regions of the North American air masses we're going to. And one of the things that we should remember that air masses differ not only in temperature and humidity, but also in stability. We know that air masses can be modified, and they're generally modified as they move from place to place. In the next several slides give some summaries of what happens with different air masses going to and from different regions. So look that over in your text relative to appreciating that situation. As air mass moves and changes with humidity, temperature, stability, etc., oftentimes fronts will develop. And we know a front is nothing more than a narrow zone of transition between air masses. That difference in density usually because of temperature. When air masses meet at fronts, generally colder, denser air forces the warmer, less dense air to rise. This, of course, induces adiabatic cooling and often brings about clouds and precipitation. The slope of the front influences the type of clouds that form. Here's an example of a stationary front. The vertical scale in this thing is greatly exaggerated, but it gives you an idea of the different cloud types: nimbostratus, altostratus, cirrus, cirrostratus. They can be formed as a front passes through. This is an example of a stationary front which generally exhibits little or no forward movement. However, many features of a stationary front are common to all fronts. As shown in a vertical cross-section, as we see here, a front slopes from the Earth's surface towards the colder air, or really the more dense air. A front lies in a trough in the pressure pattern on any horizontal surface intersecting the front. Now, a stationary front does not always have a broad region of associated clouds and precipitation as we see in this particular figure. Frontal weather can vary considerably from case to case depending upon how much water is around or the specifics of air motion relative to the front. In cases that do produce precipitation, however, the rain or possibly snow falls mostly on the cold side of the stationary front. Warm, humid air flows up and over the colder air masses, more or less along the sloping frontal surfaces. This slide gives you some descriptive components of stationary fronts and some of the discussions we have within the text itself, so look this over. If a stationary front begins moving, such that the warm or less dense air advances while the cold air retreats, the front becomes a warm front. The overall characteristics of a warm front shown here are very similar to those of the stationary front. The differences between a warm front and a stationary front are evident if we look back at the previous figure. We would see that the slope of the warm frontal surface, that is the ratio of the vertical rise to the horizontal distance, is less near the Earth's surface because of surface roughness has slowed down this warm front. Winds on the warm side of the front tend to be quite similar in both instances, but air on the cold side of the front is retreating. Thus, the warm air advances relative to the Earth's surface rather than just gliding up and over the cold air in the case of the stationary front. This slide gives us some overall characteristics as just discussed, so look this over and you can see that the wispy cirrus clouds may give us an indication that a front is coming. An air mass boundary becomes a cold front if it begins to move away in such a manner that colder, more dense air displaces warmer or less dense air. Over North American winter, the temperature contrast is typically greater across a cold front than across stationary or warm fronts. In summer, however, maximum air temperatures on either side of the front are sometimes very similar. Friction associated with the roughness of the Earth's surface slows the advancing cold air and is responsible for the nose-shaped vertical profile that we see in this particular figure. If the cold front advances at a moderate but steady pace, say around 20 miles an hour, the type of frontal weather will depend on the stability of the warmer air. Brief showers are likely as uplift along the steep cold front is sufficiently vigorous to produce a narrow band of cumuliform clouds and convective showers at or just ahead of the front. If the warm air ahead of the front is unstable, uplift is more vigorous, giving rise to these things called towering cumulus congestus clouds that eventually build into cumulonimbus clouds, with cirrus clouds blown downstream by winds at high altitudes. If well-defined cold front progresses at a relatively rapid pace, say somewhere between around 30 miles an hour, then a squall line, a band of very intense thunderstorms, may develop either at the front or as much as 180 miles ahead of the front. Later in its life cycle, an extratropical cyclone moves into colder air and a front forms known as an occluded front, or simply an occlusion. According to the classic model we see here, an occluded front forms when a faster moving cold front catches up to a slower moving warm front. There are two types of occlusions distinguished by the temperature contrast between the air behind the cold front and the air ahead of the warm front: cold occlusion and warm occlusion. Here's an example of a cold type occlusion. Cold air, cool, warm air in this region. And the next slide shows the warm type of occlusion, where air behind the advancing cold front is not as cold as the air ahead of the warm front, and this occurs in northerly portions of West Coast Europe or Pacific Northwest. This slide summarizes the information regarding fronts, and it's basically a repeat of what we've talked about. There are a couple of terms here, however. Frontogenesis, front forms and grows stronger. Frontalysis is where the front weakens, and you'll see those terms coming up as we progress in this particular chapter. So again, to define things called extratropical cyclones, which is important basically because frontal weather occurs in combination with the extratropical cyclone and is the major weather maker of the middle and high latitudes. This cyclone is a synoptic scale low pressure system that occurs in mid-latitudes, often forming along the polar front. Again, the low is characterized by fronts and a comma cloud pattern, which we'll see in a minute. Becomes a cold core cyclone, especially in the later stages of its life. So this is what we're discussing at this point in Chapter 10. These are some of the characteristics of an extratropical cyclone. Very large synoptic scale, 1 to 2,000 miles. Winds can be very relatively high. Occurs at all seasons. Frequency, lifetime, energy source, etc. are described here on this particular slide. So look this over. The diagram on the left-hand side of this slide shows the life cycle of an extratropical cyclone. A, an incipient cyclone; B, a wave cyclone; C, the beginning of occlusion; and C, the bent back occlusion that is discussed in your chapter. As a wave cyclone, the system center is located east of the upper level trough. At occlusion, the system center is under the upper level trough. and air temperatures refer to conditions at the Earth's surface. This diagram here, or this actual infrared satellite, shows the image which is characteristic of well-developed extratropical cyclones. Note the dry slot, the black shading to the south of the system center over Nebraska in this region right in here. The next several slides go through the various stages of the life cycle of the cyclone with some characteristic importance relative to each stage. So I want you to take some time and kind of look at those. They'll give you an idea as to some of the characteristics of each of the stages. The cyclone life cycle, which was just described, may occur over many days, or it may be completed in a day or so. If upper air support is less favorable, the storm may spend a longer time in any one of these earlier stages and even weaken temporarily and basically still become fully occluded. Sometimes cyclones develop with meager upper air support, that is, weak divergence loft, and are poorly defined. At other times, widespread cloudiness and precipitation are linked to an upper air or surface trough with no cloud cyclonic circulation at the surface. As with most weather phenomenon, we develop models to try to describe the phenomenon. The earlier model of extratropical cyclone formation is known as the Norwegian cyclone model, and this model was derived primarily from surface weather observations, and at that time researchers back in the late 1920s or so were unable to monitor winds aloft very effectively. Subsequent advances in atmospheric monitoring techniques, especially the remote sensing by satellite, have verified the main features of the Norwegian cyclone model. And amazingly, the model remains close approximation of our current understanding of middle latitude cyclones, even though individual cyclones may not follow the pattern directly. With improved understanding of upper air circulation in the years since the Norwegian model was first developed, we have a new three-dimensional cyclone model combining horizontal and vertical air motions. This is known as the conveyor belt model, and this model depicts the circulation within a mature extratropical cyclone in terms of the three broad interacting airstreams referred to as conveyor belts. Just as mechanical conveyor belts transport goods from one location to another, atmospheric conveyor belts transport air with certain properties from one region to another and are named for the type of air that they transport, that is, warm and humid air, cold and dry, cold or dry air. The model can be seen in this particular figure, and let's talk for a minute about this. As we talk about this model, it would be good for you to keep in mind the earlier diagram we saw relative to the source regions of the North American air masses. The idea that temperature and humidity of the air masses depends on the property at the source of its region. In the conveyor belt model, a warm airstream originates in the cyclone's warm sector and follows the warm side of the cold front near the Earth's surface, south and east of the storm center. Typically, this warm, humid air ascends slightly as it flows northward in the cyclone's warm sector at low levels. The warm conveyor belt then ascends more rapidly as it glides northward along the sloping, warm frontal surface, which serves as a boundary between the warm air and the dome of cooler air to the north of the surface warm front. As the ascending air ascends and cools adiabatically, water vapor condenses, forming clouds, and rain or snow develops. Latent heat released during condensation adds to the buoyancy of air in the warm conveyor belt. While the warm conveyor belt is gliding up and over the warm frontal surface, winds in the lower troposphere in the region northeast of the surface low blow from the east or northeast and are relatively cold. This flow forms the cold conveyor belt and at low levels is located just to the cold or north side of the warm front. Like the warm conveyor belt, this air ascends as it progresses towards the west. Warm frontal precipitation falls through the cold air stream, increasing the relative humidity to saturation so that clouds and precipitation develop from this cold conveyor belt. As the cold conveyor belt ascends, it comes under the influence of mid and upper level tropospheric winds that turn the cold conveyor belt in a clockwise direction. The ascending saturated cold conveyor belt produces the comma cloud, which we are familiar with, to the northwest of the cyclone center. Here again is the picture of the comma-shaped cloud pattern that's characteristic of a well-developed extratropical cyclone that we saw earlier. In discussing cyclone weather, these diagrams show a mature extratropical cyclone centered on the border between Minnesota and Iowa, showing typical patterns of A, the surface winds, B, the surface air temperatures, C, the areas of cloudiness and precipitation, and D, the areas of greatest positive and negative pressure tendency within a low which is moving towards the northeast. The track of an extratropical cyclone depends on the direction and the strength of the upper level westerlies in which the storm system is embedded. The low center advances at about half the speed of the 500 millibar winds. Keep in mind, however, that the upper level horizontal circulation pattern, including the steering winds, also changes with time, and the cyclone paths varies accordingly. The principal tracks of these cyclones across the lower 48 states of the United States is plotted in these diagrams. Note how cyclones tend to converge towards the northeast, their ultimate destination usually being the semi-permanent Icelandic low of the North Atlantic Ocean or Western Europe. Although many extratropical cyclones appear to originate just east of the Rocky Mountains, in reality most form over the Pacific Ocean near the Aleutians or in the Gulf of Alaska. Similarities in tracking patterns have earned some cyclone paths characteristic nicknames, including the Panhandle Hook, the Alberta Clipper, and the Nor'easter. The center of a nor'easter tracks towards the northeast along the the U.S. East Coast, and specific tracks of the nor'easters are plotted here as the Texas and East Gulf tracks. A nor'easter usually deepens off the Carolina coast and then tracks up the coast in the southwest to northeast direction. This particular diagram shows principal areas of cyclogenesis and associated cyclone tracks. Note that the dashed portions of the tracks represent specifically areas where a low may temporarily lose its identity prior to re-strengthening in the cyclogenesis areas of the coast in this case. If we go back a couple of slides, one of the things that we may remember is that the temperature of an extratropical cyclone, or the temperature areas, show that there is a cold sector, generally north and west, and a warm sector, which is generally found south and east of the low of the extratropical cyclone. Therefore, in this figure, the coldest air is northwest of the low center, where surface winds are blowing from the northwest, and the warmest air is in the southeast, where winds are blowing from the south. Therefore, an extratropical cyclone moves eastward across the continent. The weather to the left or north side of this track can differ considerably from the weather to the warm or south side or right component of the low itself. Extratropical cyclones generally develop along the polar front, and this occurs actually throughout the year. However, the storms become more intense and pose a greater threat to middle and high latitudes from around late autumn through winter and then into early spring, as the polar front shifts equatorward and the temperature contrast across the front increases. Except for the Gulf Coast and some coastal sections of Southern California, the weather of few places across this continent escape the influence of these cyclones and the winter storms that they produce. A winter storm is an extratropical cyclone that produces some combination of frozen or freezing precipitation, including snow, ice, freezing rain, and other things we have studied in earlier chapters. One of the more severe storms is defined as a blizzard, which is characterized by high winds and reduced visibility due to falling or blowing snow. A blizzard requires sustained winds of about 35 miles per hour or greater and sufficient falling, blowing, drifting snow to reduce the horizontal visibility to less than a quarter of a mile. This next slide represents a schematic representation of a surface weather map showing the various forms of precipitation associated with a mature Colorado track winter storm system. Everything from snow to thunder showers to freezing rain and even rain and squall lines can be seen in this particular schematic. As noted previously, the circulation in an extratropical cyclone favors convergence of contrasting air masses and developments of fronts, clouds, and generally precipitation. In contrast, an anticyclone has subsiding air and diverging surface winds, which favor the formation of a uniform air mass where there are generally no fronts and relatively fair skies. Like cyclones, anticyclones have either cold or warm cores. A cold core anticyclone is actually a dome of continental, polar, or Arctic air, and cold anticyclones are produced or are products of extreme radiational cooling over the snow-covered continental interior of North America within the United States and Canada. Cold core anticyclones exert the highest pressure in the winter. This sets up extremely stable conditions within this particular anticyclone. Warm core anticyclones form south of the polar front and consist of extensive areas of subsiding warm, dry air. Because subsiding air is compressionally warm, the relative humidity drops, and clouds usually dissipate or even fail to develop in this anticyclone situation. We've been talking up to this point about synoptic weather systems that dominate weather outside of the tropics. There are many other weather systems operating at smaller spatial and temporal scales, which also contribute to the mix of weather and climate of middle and high latitudes. In the next few slides, we open our discussion of mesoscale and microscale systems with sea or lake land breezes, mountain and valley breezes, Chinook winds, and Santa Ana winds, as well as katabatic winds and desert winds. Each of these local and regional circulation systems are fairly self-explanatory. Valley breezes, mountain breezes, Chinook winds, Santa Ana winds, and the patterns that are associated with them for local and regional circulation systems. So I'll ask you to look those over by reviewing the slides and your text associated with that.